d of r naught is y minus tx. So d of oh wait, but before we do we really need to? Yes, I think we need. See, this entire calculation is based on the fact that r is not equal to 0. I mean, if r is non-zero, then only we are getting this inequality. So before I use that here, I should be able to make sure that r is non-zero, because here non-zeroness of r naught allows me to write dr naught. However, I cannot say that this is less than dx unless I make sure that r is non-zero. Okay, so let us try to conclude that r is non-zero. Assume r naught is not equal to 0. Then r, what is r from here? R is y minus tx times x bar. X bar, which is nothing but r naught x bar, is also not equal to 0. And why is that so? R naught is non-zero, x bar is non-zero, because x is from the very beginning, x is non-zero. So its complex conjugate is also non-zero. So their product is non-zero. Now we can write, hence d of r naught, which is d of y minus tx, is strictly less than d of r. So what have we achieved? See, y is any Gaussian integer, x was any non-zero Gaussian integer. We have been able to write y as tx plus r naught, where t and r naught of course are also Gaussian integers, and either r naught is 0 or when it's non-zero, its d value is, this will be x, no? Y minus tx is less than, yes, x. Its d value is less than that of x. So that is the general case. This completes the proof. So we have now proved that Ji is indeed a Euclidean ring. So all the results about Euclidean rings are going to be applicable to Ji. In particular, we have that result that every ideal is a principal ideal. In Ji also that will be true. Okay. So now, having achieved this feat, we are now next going to see a number theoretic result, which however will be proved using the ring theoretic ring structure of Ji. So this is Lemma 381, and this lemma will take us towards that, will lead us towards that result that we were talking about from number theory about prime numbers due to Fermat. The lemma states this: let P be a prime integer, that is P is an ordinary prime number, and C be an integer relatively prime to P. Let, or instead of writing let, suppose Cp is equal to x square plus y square for some integers x and y. Suppose it happens that the product Cp can be written as a sum of squares of two integers. Then P is a sum of two squares. P itself is a sum of two squares. That is, there exist integers a and b such that p is equal to a square plus b square. Okay, this lemma will be needed in our in the proof of the main number theoretic result. So let us now prove this lemma. Okay, so P is a prime, C is an integer. Note that the ring of integers is a subring of Ji. J is contained inside Ji, that is obvious, but it's also a subring of Ji. If we apply the addition and multiplication that we have, just like the ring of the field of real numbers is a subfield of the field of complex numbers, in that sense the ring of integers is a subring of the ring of Gaussian integers. Now observe that, let us start our arguments from this equation. Observe that Cp is equal to x square plus y square. This can be written as x plus yi times x minus yi. You can view this equation as an equation in Ji. Since x and y are integers, both of these complex numbers x plus yi and x minus yi are Gaussian integers, and so are c and p, because after all they are also Gaussian integers, being integers themselves. So this can be regarded as an equation in Ji. Suppose the prime number p, which is a prime element in the ring of integers, is also a prime element in the ring of Gaussian integers. It may not be. You see, 2 is a prime number in the ring of integers. However, 2 is not a prime number in the ring of Gaussian integers. Why? Because 2 can be written as 1 plus I times 1 minus I. And none of these Gaussian integers is a unit. For them to be unit, they should have their multiplicative inverses also in the ring of Gaussian integers, which is not the case. So although 2 is a prime number, ordinary prime number, as a Gaussian integer, mysteriously 2 is not a prime element. So it may happen that we may come across a prime that is not prime in Ji. However, suppose P is a prime element in Ji, then what does this equation tell us? It tells us that P is dividing a product of two elements. So according to a result we have proved in the theory of Euclidean rings, P has to divide at least one of them, and that result specifically is this. Then Lemma 376 implies P divides x plus yi or P divides x minus yi. Okay, one of these two things has to happen. Oh, divides where? Where is it dividing? That also I should mention. In Ji, when you say that an element is dividing another element, where that division is taking place, that has to be mentioned in Ji, which means that when you are writing this x plus iy as P times something, that something will come from Ji. That's what we mean, because you see it matters, the background ring matters. We cannot divide 2 by 3. 2 does not divide 3 in the ring of integers. However, 2 actually divides 3 in the ring of real numbers. This may sound quite strange, but it is true. Why? Because here we cannot write 3 as a product of 2 and something, that where that something is coming from the ring of integers. However, here that can easily be written. Here that something is 3 by 2, which is a real number. Okay, so the background ring matters. Okay, in Ji, assume P divides x plus yi, then x plus yi is equal to P times u plus vi for some Gaussian integer u plus vi. This implies, okay, now if we equate the real and imaginary parts, we would get x equal to pu and y is equal to pv, and so P also divides x minus yi, because x minus yi is just pu minus pvi if this happens. So P also divides x minus iy. Similarly, if P divides x minus iy, then P divides x plus iy. So if one of these two is true, and which they are true, if our supposition is true, then one of them is true, then both of them are true. Hence, okay, what do we get from this situation then if this happens? Hence, in that case, okay, then P divides both x plus iy and x minus iy. So P square will divide x plus iy times, it will not look good if I write it here, P square divides x plus iy times x minus iy, which is equal to Cp from here, or P divides C, because if P square divides Cp, then you can argue and get this relation that P divides C. This contradicts the hypothesis. You see, the hypothesis is that C and P are relatively prime. So in particular, P cannot divide C. P should not be able to divide C. So this contradicts the hypothesis that the greatest common divisor of P and C is 1. That means our supposition is wrong. That is, P is not a prime element in Ji. How strange. But as we have seen an example that 2 is not a prime element in Ji, just like that P is such a prime number. Now, since P is not a prime element, so it has to have at least 2 non-trivial factors. Thus, P is equal to A plus Bi times say G plus Hi, where A plus Bi and G plus Hi are both non-unit elements. Or non-unit elements, I should not write elements, are both non-units in the ring of Gaussian integers. Okay. Now, if we take complex conjugate of P, since P is after all a real number, it equals its complex conjugate. However, here the complex conjugate gets distributed over the product. So we get A minus Bi times G minus Hi. So what will be p square? P square is p times p, but once we are using this expression and once we are using this expression. So p square is equal to a plus bi times g plus hi times a minus bi times g minus hi, and if you take the product it will become a square plus b square times g square plus h square. Okay, now note that because a plus bi and g plus hi are Gaussian integers, so these are integers, ordinary integers. This implies the integer. Also note that none of them is 0, because then p would be 0, which is not true. P is a prime number, so it's non-zero by definition. This implies the integer a square plus b square divides p square, because p square is a multiple of a square plus b square in the ring of ordinary integers. But because p square has only 3 factors, so a square plus b square can be any one of them. Thus, a square plus b square is equal to 1, or p square. Note, okay, now we are going to use the fact that these are neither one of them is a unit, neither of them is a unit, both are non-units. Since a plus bi is a non-unit, we have a square plus b square not equal to 1. It's a fact that if we find the d value of a non-unit in the ring of Gaussian integers, then its d value is not equal to 1, and this is exercise 2 at the end of this section. We will show this there. So a square plus b square cannot be equal to 1. Also, since g plus hi is a non-unit, just like that we have g square plus h square is also not equal to 1, and hence a square plus b square is also not equal to p square, because if a square plus b square is p square, then g square plus h square has to be equal to 1, which is not possible because it's also not equal to 1. So a square plus b square can neither be 1 nor p square, so there is only one possibility left. So the only possibility is a square plus b square equal to p square, p. So that's how we have realized p as a sum of squares of two integers.